Today we're going to talk about some of the topics in the next section of our textbook, and the topics are a little bit varied. We've got partition matrices, and we also have matrix inverses, by which I mean multiplicative inverses for matrices. And the thing that they have in common is that they're both useful for thinking about solutions to a linear system. So let's think about this little linear system here. We've got x plus 3y equals 0 and 3x plus 3y equals 4. And we could do something like elimination and substitution to figure out what x and y should be. If we write it via matrix multiplication, which we've talked a little bit about, we get a coefficient matrix A, we get a vector of variables with x, y in it, and we get a scalar vector, like a vector on the other side with the b's that we're setting our equations equal to. And if we could figure out A inverse exists, then A inverse times A is the identity matrix. And we get something like, we can do a few steps of manipulation and we'd get that X is the product A inverse times B. And so that's one way that we could solve this equation. We could figure out what's the inverse of the matrix A and use that to get the solution set. There's another way that we can solve this system, and it requires us to define a new type of matrix. We could just take A and B and smush them together. I know it's really technical, but this is essentially what we're doing. We're taking A and we're tacking B onto the side of it. And when we do that, we often have this little dividing line in our notation. It doesn't change the fact that this is a 2x3 matrix, but it does help us remember where these original matrices came from. I'll just say quickly, there are other ways that you could partition a matrix. You could say like, oh, I've got this matrix and I notice that it sort of breaks up into, some A and B, and then I've got some 0 matrices over here. So partitioning a matrix is really just a way of talking about submatrices that you could identify living inside your matrix. The most common ones we'll see look like the partition matrix AB, and sometimes we'll think about the partition matrix A, and then we tack an identity matrix on the other side, and we do something to the matrix to figure something out. That's a little bit vague, but we're going to get there. So why do we want to write down these augmented matrices? Well, we're going to see that there are things that we can do to them in chapter 2 of our textbook to find solutions. We're also going to find that we can just very concisely write down a linear system as one single matrix and just refer to that single matrix to refer to the linear system. So here's an example, and it's also an application of the matrix vector product theorem, the MVP. So this theorem says that for any m by n matrix A and any m by 1 matrix B, the linear system AB is consistent if and only if B can be expressed as a linear combination of the columns of A. So if you hear the words linear combination of the columns of A, that should ring your MVP mental bell. We should expect that, the MVP is going to come into play here because the MVP is about linear combinations of columns of a matrix. So let's go through this proof, and I'll highlight some of the big pictures before we get into the details. Of course, our first line tells us what size matrices we're working with. I've introduced the matrix X so that I can have, the vector of variables to do matrix multiplication with. And I see that I've got these two arrows in my proof. This indicates that I'm proving a theorem that really has two statements. One of them is AB is consistent, implies that B can be expressed as a linear combination of the matrix of the columns of A. And the other says that B can be expressed as a linear combinations of A implies that the linear system AB is consistent. So we've got two pieces of work to do. And as a reminder, we'll talk more about that when we talk about formal logic next week. So let's start by assuming that AX equals B is a consistent linear system. And that means, this is a reminder, that there is at least one solution. Where setting x1 equals c1, x2 equals c2, xn equals cn, where all of those are real numbers, makes this equation true. makes these equations true. Right, so we've got at least one solution. That's what it means to be consistent. And that means that when we apply the MVP, we know that A times this vector with the C's plugged in is going to be B. So that's our first equality. And the MVP tells us that we can rewrite that product as a linear combination of the columns of A, where the scalars are the C's and the columns, and they, get multiplied by the appropriate columns of A, and we add them together. So that takes care of that direction. And on the other hand, let's assume that B can be written as a linear combination of the columns of A. And this means that there are scalars C1, C2, Cn, where B equals C1 column 1 of A plus C2 column 2 of A plus blah, 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 plus Cn column n of A. And now we're going to apply the MVP, but using the equality in the other way. So we've written down B as a sum of these columns, and we know we can repackage that as matrix multiplication, which looks like A times this vector C. And that means that this vector of variables X, if we plug in the C's for the X's, we get a solution to AX equals B, which means that the system is consistent. It doesn't necessarily mean that's the only solution. It could have more than one solution, but it does tell us there's at least one, and that's what we need for our system to be consistent. So this is, really more of an application of the MVP than anything that's trying to sell you on partition matrices, but it's really nice. Notice in the statement of the theorem, I don't have, this is a pretty concise way to refer to my linear system. But here's actually why we like linear systems. So if we had taken our equations up above, and let me remind you what they were x plus 3y equals 0 and 3x plus 3y equals 4. I think that's what they were. We could do, whatever steps we would do to solve this system of equations. I might add -1 times equation 1 to equation 2. And that would eliminate y from equation 2, and I'd get 2x equals 4, and then I could solve that for x to get x equals 2, and I could plug that back in and get y equals -2/3, assuming I did my arithmetic correctly. It turns out that we can do all of those procedures to our partition matrix, and that's something that we'll also talk about in chapter 2. But you could imagine, instead of working with equation 1 and equation 2, we could work with row 1 and row 2, and do things to those rows to come up with an equivalent system of equations. And equivalent means it's going to have the exact same solution set, so that if we find a solution set for this system of equations, we know we've got a solution to the original system. And we're going to play around with that idea a lot. But this is, if I think about what I just talked through with those equations and what I've written in this paragraph here, I can capture that by telling you what I'm going to do to these rows. And I've indicated my rows with R sub 1 and R sub 2. So I might take row 1 plus -1 times row 2, and I could add that to row 2. Is that actually what I wanted to do? I think I actually, I want to take row 2, and I want to add -1 row 1 to it to be consistent with what I did before. And that actually looks correct, right? So I'm going to subtract 1, 3 from 3, 3, and I get 2, 0. And then I take 1/2 of row 2, and I get a new row 2 that way. So I get x equals, and I can read this as saying, like, this is sort of telling me about the x's. This is telling me about the y's. This says x plus 0, y equals 2. So x is 2. And then 1x plus 3y equals 0. And that's how I get my y equals -2/3 up above. And there, we actually could, continue doing steps to get all the way down to something where it looks like, 1x is 2, so I'll put some dots here, and 1y is -2/3. Sorry, you can't read that, but And that's one way to find the set of systems to linear equations. And this is something that's coming up, but I wanted to preview it for you because it's kind of a cool idea. And it takes the ideas of elimination and substitution and turns them into things we can do to matrices. And these steps are called row operations, and they're the content that we'll cover in chapter 2. One more thing about row operations, we've seen that we can think about a linear system now in 2 ways. We can think about it as an augmented matrix, and maybe we do some stuff to the rows of that matrix, or we can think of it as a product of a matrix equation that has a product in it. So probably there's going to be a way of understanding these row operations in terms of a product of some matrices, and that's also a really cool fact. So the moving back and forth between partition matrices and matrix equations is a really neat way of doing mathematics, and it sort of allows you to decide like which way is more useful to me at this moment with the thing that I'm trying to do, and how do I translate back and forth if I decide I want to try it the other way as well. Okay, so at our next class we will talk about multiplicative inverses. The idea of a multiplicative inverse is pretty straightforward. It's a thing that you can multiply a matrix by to get the identity matrix. And we'll go through some examples of those.